All right, so as I was saying, welcome back from our long vacation of Memorial Day weekend. So this is, we started this lecture. I know we started this lecture before the week off. I should say day, it was really a week off. So I don't know where I stopped, but instead, slide number 4. Oh, then that's not too many slides. All right, so what I'm going to do is sort of pick up where I left off, but I think I'll just start with the process concept here, which is slide number 3. I'll start a slide early, because processes are sort of an important concept when it comes to operating systems. So I want to make sure you guys get this concept, and this is all about assignment number 1. So for those people who worked on assignment number 1 over the little break we had, are probably familiar with the process concept already in threads. If you didn't work on it, then just know it's the hardest assignment in this course. So all the other ones will be a lot easier. So don't judge that first assignment as representative of all the work you'll have to do for the other assignments. The other ones are so much more easier than this one. So the process concept, every operating system has them. They are a process, by definition, is the running program. It's a program that's running. Programs, until they start running, are not processes. They are just saved files on your computer. And so threads run inside of processes. So that's where we get thread concept. Some people actually think thread and processes are the same thing. And by some definitions, they actually are. A thread of execution, a process. But they're really the same concept with two different abstractions. The kernel thinks of them as threads. The user thinks of them as processes. So when you go to program your first assignment, you might be thinking, oh, how do I make a process? She said something about processes, But then you'll be creating threads. So you'll be forking a thread. But a thread and a process in that context is the same thing, essentially. So don't get too concerned with the differences between threads and processes. Some books actually say that threads are lightweight processes. Some people say they're the same thing. I want to call them the same thing, but I usually refer to kernel threads and user processes, if you want to remember it that way. It's probably a little bit more universally used that way, but there's a lot of confusion in the concept. So operating systems that execute programs in a batch system or a batch process, those are called jobs, and those jobs run one after the other. They don't run simultaneously. And that doesn't really necessarily need too much process sophistication to it. We just create one job, another job, another job, and things run sequentially. Processes have really become a feature of operating systems since the multi-processing and multi-threaded programs come into place. So if we take a program and we break it out into separate different processes and we run them, then we can spread the work out among multiple different memory areas. Because I remember, I think I probably gave you the memory layout, but we'll talk about that in a few minutes of a process. Processes are just stored in RAM. So in the memory, it's really just an abstraction of memory that's being used by the computer. And CPU scheduling goes into that memory location, pulls the process instruction out of there, runs it, puts it back. So it's constantly reading and writing to memory, and this is the RAM memory, not the hard disk memory. So the textbook uses jobs and processes almost interchangeably. So I don't like the word jobs, so I won't use that, but I'll call everything a process. But a process and a job, by definition, are also kind of the same thing. In a batch system, we have jobs. In a time system, we have user programs or processes or tasks. And a time-shared system means more than one user is using the system, or more than one process from different owners is running on a system. And then we have the multi-threaded, where we have a program that has multiple threads inside of it that's taking up more resources, but it's running faster. So all the pieces will come together, I hope, as we go through. So the textbook does use the word jobs, and the process itself is a program in execution by definition. So this bullet point down here on the bottom is a nice little definition of a process, the one that's on the top of the screen right now, this one. It's a program in execution. A process execution must progress in a sequential fashion, and actually processes are sequential. Even though we have this illusion of there being multiple things going on, the program really is just running line by line by line. It's not really running in parallel with anything else, because at any one moment of time, only one process is running on the computer system. So the process includes these three components to it: process, program counter, stack, and data section. And here's probably where I stopped, actually. This is the process abstraction in memory. And we have this concept of the stack, and we have the concept of the heap, the data and the text. So let me just explain, I can explain to you what these different sections are actually a lot easier than showing a bunch of slides on it. The stack is holding all the program instructions that are going to be executed. Well, isn't that really the text? Yeah, it is. So I actually draw this upside down. I put the stack here and I put the heap up here. Some textbooks actually reverse it as well. This is all memory, however. So when we double click on a file in Windows or exe file, we're not going to read and write back to the file. We're just going to take the whole file and we're going to load it up into memory. Well, it's going to be on the bottom, and that's going to be the text. So the text is kind of deceiving. It's really the text that's coming from, the information that's coming from that file. We're going to load it up in the memory. And then we're going to have data that's going to be allocated from the stack. Data, well, let's see, if we wrote a program in C and we said integer I would be holding an integer value when we're going to use this data. Sometimes people call this static data because it never changes. We always have i's in the instruction set. And then we have the heap, which is also data section, but it's dynamic data. So when we say new pencil or new something or other, and we use new int, and then we dynamically allocate memory, this is the dynamic data. So static data, dynamic data, which is why the textbook sort of puts this together, lumps the data together. The heap grows into the stack grows into the heap. So if we create, let's say for example, a recursive function and we don't end it, recursive function is going to add stack entries, add stack entries, add stack entries. We generally end up with a stack overflow error because of that. Or let's say we program and we use new and we never use delete. We allocate, allocate, allocate. Create a little loop, just allocates memory constantly. Well, we're going to have memory segmentation faults because we're going to try and write into memory that doesn't belong to us inside of the process. Now, if this process crashes, nothing on the computer crashes, just the process crashes, which is kind of an interesting concept. So you can't really crash your computer by a bad process, but you can crash the process. The program can end, actually. So we have different process states. So imagine if you wanted to take a picture of a process that looks like this. Well, does it really look like that? Memory doesn't really look like that. I don't even know what memory actually looks like. But this is sort of an abstract representation of the process. Now the process can be in any one number of states. We have new, running, waiting, ready, and terminated. And the process changes. Think of it like a life cycle of the process. It changes these states until it finally terminates. So at the beginning, it becomes new, and what I'll do is I'll show you this one here to actually kind of give you the process here. Everybody starts as new, and then when the process is over with on the exit, everybody terminates, and we're done. So from a new perspective, we get admitted into the process queue for process. So this is how processes actually work with scheduling. So in the next chapter further down, students have problems with two areas, processes and CPU scheduling, generally, for operating systems. That's like the biggest complex, and memory management, complex areas of operating systems. It's really not that bad. It's only because they have multiple pieces working together. When you load the process up in the memory, and you get this, whoops, you don't get much. You just get a piece of memory, and now you got to do something with it. So that's where the process scheduler comes into place. And the process scheduler changes the states of the process. So when the process is created, a little stamp on it says, hey, I'm new. Well, where's the stamp go? It actually goes in this thing called a process control block. So we have a data structure that the kernel keeps track of all the processes with, called the PCB, short for process control block. It's keeping track of number one item right here, process state. So it's keeping track of all of the different states that these processes are going into. Why do they need to change states? Well, it's almost like they need to be animated. They need to do something. If they're just statically just loaded up into memory, my program's not going to run. So I need to run the program. So the process is new, it gets admitted into the system, and then it becomes ready. It's new when we're just allocating the memory and we're loading the data in there and we're filling up the stack, we're new. Then when we're all ready to go, we get our label changes, our state changes, and now we're considered ready. And then we switch back and forth between two different states before we finally terminate. So if we're ready, we're either going to be running or we're going to be waiting. Or we might actually go back into ready before we even start running or waiting. So one process goes into the queue, and I say queue because this is like CPU scheduling queue. The information goes into the PCB, so process control block is keeping track of this stuff. And we have a CPU queue that's keeping track of all of the CPU power. Everything, the first thing a process does is it gets CPU time. Everything gets CPU time. Then we have separate I/O queues for all of the different things that happen. What's an I/O queue? The USB drive, the CD-ROM drive, the hard disk, everything that's input-output I/O has its own separate queue normally in modern day systems. So we get the process, it comes into the ready queue, and the ready queue is going to be probably a short-term scheduler. And I'm going to get into CPU scheduling later on, not today, but just take the vocabulary at this point. It's going to be a short-term scheduler, which means it's just going to sit there long, very, very short. So most CPU scheduling is done with a multi-queue tiered algorithm, where we have short, medium, and long. So a short-term one is every process goes into it. Why make the queue big? If every process needs CPU time, let's just make it what's called a short term. It doesn't stay in there very long. Instead, it goes into the medium or goes into the long. Oh, you're I/O bound, I'll put you in the long queue. Oh, you're just going to do hello world, we'll put you on the short queue, medium queue, or leave you, actually just process you out from the short queue. So the scheduler determines the priority, what you're doing as a process, and then it'll rotate you around in different queues, but your state changes. So your state is when you're getting CPU time, you're running. Means you're the one that's running, and then you only get to run for a certain amount of time, then you're interrupted. Usually there's an interrupt. This is an interrupt driven process. So the kernel sends an interrupt out, say stop, stop. All right, save all your information, put you back into memory, save your state, which is the program counter. So if we go in here, what do I got in here? The next item is the program counter. So I'm kind of giving you the process control block format as well as states all in one here. So now we've moved to program counter. So from process, because line number 1, line number 2, line number 3, oh, stop running, let's go back over here. So then the program counter gets changed to say, hey, this is where we stopped. Because next time we get CPU time, we're going to go, okay, line number 5, line number 6. We're going to pick up where we left off and then update the program counter so that we know where to stop next. If we're not running, and we're not ready, we could be waiting. Like we ran, and it said, oh, you need to use the USB port. Okay, so we get moved into a separate queue, and we gotta wait. Okay, waiting for I/O. So we have an I/O or an event wait. We're waiting for the disk to become ready, or we're waiting for something, some resource. If we're waiting for a resource and we can't run, why keep sticking us back into the run state? So we switch the state to waiting, so we don't waste CPU time, and then, which is called busy waiting, checking to see if we can run yet. Can we run? Can we run? We can't run. So we're going to get a separate interrupt that's going to occur that's going to say, okay, hey, the USB device is ready now. So who's waiting? You're waiting. Okay, interrupt wakes up the process, and so they're no longer waiting. They did their I/O, then they're back into the ready queue. And then they can go and run again, go back into the ready queue. So we have the scheduler or the dispatcher that dispatches the scheduling. So this is maybe a separate queue, that might be a separate queue, who knows. We have the I/O event or something that completes, that brings us back into the ready queue. We cycle around indefinitely until this happens. Exit. In fact, that's when you can do the exit 0 or exit something, you know, in your C program. It's a system call actually, and the system call says, okay, terminate, exit, terminate, we're done. We're done processing. We don't want to keep too many of these processes running if they're done, because then they constantly get checked. So, which is kind of interesting. You might notice on your Windows systems, actually, your computer will run faster if you load programs, one program up, stop the program and load another program up. So run one program at a time. Don't have like 5 versions of Word opened up. Your program actually runs faster because it's getting more CPU time. There's fewer items in the queue that it keeps having to go through. And even though it's just sitting there, minimized, it's still checking CPU time because it's constantly being checked. What's it waiting for? Well, it could be waiting for user control. When you minimize something, Windows automatically lowers the priority, puts it down into a separate queue, so that when you click on it, it takes longer. actually, because it has to load back up, switch the queue back over into the other queue, and then it starts running at full speed. So it's kind of interesting if you notice the user's experience. And that's the other interesting point to make as well. Operating system design is for everything. It's for user experience. It's for the best efficient or better quality use of the hardware. It's for the advancement of the computer applications and programs. There's a lot of driving factors that go into the design of this game. Well, we also have CPU registers. We have who's using the registers that are associated with the CPU, and I have to talk about memory in order to actually kind of get into that concept. But imagine a hierarchy of memory, and we have these registers that are located really close to the CPU, which is kind of temporary caching area. We load stuff in, we load stuff out. We want to recreate that. So the stuff in the process control block is all for recreation. If we had to take a snapshot of what's going on right now and save it for later, for each one of the processes, that's kind of the information. So what kind of CPU registers were there? What CPU scheduling information was there? Were we almost ready for the IO queue? What kind of stats or whatever we were keeping on that? Memory management information. Yeah, that'd be like, where are we in memory? We need to know where the process is in memory so we can go back there and find it again. Accounting information, you know, who owns the process, what time was it started, how long has it been running, and then IO status information. You know, are we IO bound process or are we like a CPU bound process, stuff like that. So the process control block keeps track of all of the information that's associated with each one of these processes, which are nothing more than an abstraction of memory. And that abstraction of memory floats between these different states, and it gets CPU time, so it looks like, you know, a whole cycle of activities that occur for the process, and then it's terminated. So usually the first question that some students actually kind of think about in this point is they go, well, why do we keep track of all this stuff, and why do we want to bother then? Why do we want to bother with all this stuff here? Can we just run the process and just execute everything? Why do we have to go through this elaborate scheme? And the answer to that question would be, well, because of the user experience. If you're only able to run one program at a time on your computer, that might not be a good thing. So you want to load multiple programs and you want to have everything running simultaneously. Well, in order to do that, you have to have a scheme. You have to have something like this going on. So. Alright, so let's see what we got going on here. Here's the process control block. If I were to look at a memory abstraction of this, it would sort of look like this. What do I mean by that? Well, I got the process state, process number, program counter, the registers. What is that? It's just memory. So we got another piece of memory that's formatted for each one of the processes. So you might imagine why we need so much memory on the computer. So most people go, I don't know what this RAM is used for. Holds all the processes, holds all the scheduling information. Your operating system uses more memory than you do, which is why you open up the box of, what is it, XP that required 2 gigs at one point. I don't know how many, 7. I don't think you can run on less than 4 gigs these days. I'm not sure. The memory requirements keep going up and up because all the operating system keeps getting heavier and heavier. They want a lot of memory. So what does it mean when you have 8 gigs instead of 4 gigs? Well, you just have extra memory. Not always a good thing. In fact, some computers with smaller memory footprints run faster. And you'll see that when we get to the memory management section of this book, or this lecture series, because, well, okay, so if I have 4 gigs and the operating system needs 4 gigs, I'm going to need something on top of that. So I think most operating systems need about 3 gigs, and then they have 1 gig or so for user programs. So it gives us about a 4 gigs, 6 gig kind of requirement. Well, what does that mean? Well, if we put more memory on there, can we load more programs simultaneously? Yes, because you have more memory space, which means there's less loading and unloading going on. So the way memory management works is that each one of these processes, and I'm going to briefly describe this, we have an entire lecture on this, but all these processes are loaded up into memory, and then eventually we're going to run out of memory. So then we have a routine called a memory manager, routine that goes up in there and teaches, well, here you're here, okay, we'll put you on a backing store, we'll make room for somebody else to come in. So there's different priority schemes to it, there's different configurations where at one moment of time we might have more programs loaded than we have memory space for. So we might have like only 1 gig and we have like 5 gigs worth of data, and we keep shifting things. So memory manager shifts things back and forth, which is why the memory management information is stored in the process control block. It needs to know, are we loaded into memory? If we're not loaded into memory, go find us, load us up back into memory, switch something out. So it's called swapping, actually, when we swap things in and out of memory. The more swapping you have, the slower things load, the slower execution, so the people say, put more memory on. There's a fine line though. So if you add more memory to your system, you have less swapping going on because you can hold everything into memory, right? But think of the bad thing about that is that you have more memory to search. Because the first thing it's got to do is find it in memory. So if you have a huge search space and you're not using it, waste of CPU power. You're spending so much time searching through memory you don't need. That's empty, but you got to look for it. So that search inefficiency slows your system down. Well, so there's a fine line between, well, you have to have a little bit of search inefficiency because you want that memory available so you can minimize your swapping. And then you go, well, which one is faster, swapping or searching? Swapping is faster, actually, especially if your system's got cache on it. Because if you got a cache system set up, and a cache is just a little bit higher grade memory, that's faster. It's stored closer to the CPU. So in memory, everything that's closest to the CPU runs faster. So the farther away you get, which is your RAM the farthest memory away from the CPU. Swapping is kind of slow, so you cache. What that builds is it increases your memory footprint, but makes it more efficient, and it's used just for swapping. So if you're not doing any swapping, you're not using your cache. So you buy a fancy system that's got a ton of cache on it, you load on 16 gigs of RAM, probably never going to use your cache. Your cache is to make the swap. Your cache is supposed to be making your swapping run faster. But if you're not swapping and you're spending so much, you could actually take a configuration and make it run slow. And it'll be the most expensive computer you've ever bought, but it runs slower than like one of those cheap ones does. Because, well, the other thing is the CPU. But yeah, if you have one CPU, so the best system is to use just enough RAM but not too much RAM and have caching on your system. So make sure you got a good size cache on that system with minimal, so if the operating system needs 4 gigs, you want to like maybe 2 to 4 extra gigs, no more than 8 gigs on that sucker. So a lot of computer manufacturers know this, and so they go, well, let's talk about hardware first. You take a computer architecture course, and they show you the combinations, because it's all about the combination. So you want to have such and such cache, such and such memory support, because the memory support is going through what's called an MMU, and the MMU is what's being read by the kernel, actually. So you configure all the pieces to make it cost efficient, because everything has different, if this is a little bit cheaper than this, you get a little bit more of that, you minimize this, and you put it in combination, because you're also concerned about battery life on these suckers, because everything's portable these days. And the more RAM you have in your system, believe it or not, the more battery it uses. So even though you've upgraded to 16 gigs, you've maxed that board out completely, which I'm saying don't do that. Don't max your memory out. It's not going to give you anything. What are you going to need it for? Web browsing? Checking email? You don't need it for that. So it also cuts down the life of your battery, because the MMU is going to take up more memory because it's got to go through more chips. It's got to look for more stuff. So if you want to conserve your memory, don't put the memory on there. I mean, conserve your battery. But anyway, long story short, it's all about the configuration. It's all about putting the pieces together in the right combination to get that hardware working. If the hardware is not working efficiently, the operating system can't help it. Operating system is going to be slowed down or sped up depending upon the configuration of the hardware. So certain systems change with certain operating systems, which is why you always get them in parallel. So you get brand new operating system, brand new hardware system, different configuration. So then they usually say on the box, only works on this processor, only works on that processor. And then when they sell new computers, they always put the latest and greatest, and then people go, oh, I don't want that operating system. Well, you don't want that. You go back to a previous one. You're not taking advantage of all that good hardware you just bought, and your hardware configuration isn't matching your software, your operating system. So the other second piece of advice, for number one, make sure you have enough RAM, but don't max it out. Number two, make sure you keep the operating system that the manufacturer decided should go on that hardware. Don't switch the OS, which people don't do anymore, but you know, people were upgrading Vista to something else, and they were upgrading XP to 7. Don't do that. Just buy another computer. Because you're going to have a system that's going to run too slow because it's not optimized correctly. So anyway, the other trick they did is if you talk about process control block and CPU scheduling, the way you make this faster, you add on another CPU. But you don't add on a dual core, you add on a dual processor. So you have not a core that's separated out into two chips that's working together as one, that is working as one in this system. You want two. If you get two, then you have to have an operating system that's designed to use it. So then we have two simultaneously running CPUs with two schedulers and two routines, and we have it divided out correctly. So user programs will run faster because it's not waiting for the OS level stuff to run. That's on a separate processor. So you have a lot. So when the dual processors, not the Core Duo, but the real dual processor came out, that really solved a lot of problems. What they did with the Core Duo is they took two inexpensive processors double in speed every year, according to, I can't remember the name of that law, but there's a law of computer science that does that. Murphy? No. Somebody knows it. Someone's saying it. It's some IBM guy came up with this. But anyway, long story short, I don't remember it, but doubles in processing power every year. So if you're growing too fast and you're not selling enough computers, because when the dot crash in the economy, computers weren't selling that great, right? So now you take two, you got excess processors. So they had an abundance of processors, so they took them and wired them together to make them faster. So instead of having, if you have like a 3 gigahertz, you know, now you have a 1.5 and a 1.5. Put it together and you get a 3. Which is why some of the, in fact, Compaq was really doing this. This is back when Compaq was alive. You could buy like a dual processor Compaq computer, and what ended up happening was it's cheaper than the single processor ones. Well, yeah, because you got half the power soldered together, working together as one unit, slower than if it were just one chip because of all the communication back and forth between the two of them. And then the memory footprint went up because you have to keep information. Extra information needed to be stored about the two. You had to have way complicated CPU scheduler, way complicated process scheduler, whatever. Long story short, some of those systems had like 4 gigs of RAM on it and 2 processors and this and that, but it ran slower than like an old x86 computer. I mean, like the old, like the 386, 286s, which is really old actually. And long story short, it's the configuration and then it's the processes that are designed to run with it. So let me talk about 32 and 64-bit processors and systems. So if you have a bigger memory here, if you make that bigger and then you make this faster, you've also increased the speed. If you make this faster and you keep this the same size, you haven't done anything. Which is funny because people take 64-bit systems and they try to install 32-bit software on it all the time. I'm like, why don't you just use it on a 32-bit system if that's the case? You're not utilizing your processor speed. It doesn't really matter how much faster your processing is going on. Your memory footprint's the same. You have the same number of stack entries coming into there. You have the same processing going on as if you were working on a smaller, slower processor with slower memory footprint. So. Anyway, not a hardware class, but just another example of what happens. So if you have a 64-bit system, run 64 everything. Don't downgrade to 32-bit and run it in a 64 mode or something. It doesn't work. So. All right, so this is the process control block. It's memory abstraction. And here's our CPU switching from process to process, which is what I was talking about. And I've kind of described already, so let me show you a picture of it. This is called CPU scheduling. This here says CPU switch, sometimes also referred to as context switching. So context switching is CPU switching. It's part of CPU scheduling. So context I like to use the word context instead of CPU switch because it's really the context. What is running? So is the CPU is not switching. The process is switching. The context of which process is switching. So we have process 0 and we have process 1 over here, and they're both sharing the CPU simultaneously. Now this is simplified. In any one moment of time, we might have 50 processes. Actually, just go open up, what is it, Control, Alternate, Delete, open up the list of processes on the system through the, what is that thing called? The Task Manager. And then you can see, I'm not hip on Windows, you can see all the running processes on your system. You can click on one and delete it. You can restart one. You can see which ones are dead, which ones are idle. That's what this is talking about. So we have an executing, and this is the execution. It starts at the top and it's going down this way. This one starts at the top and it's also going down here, and we have idle time. Well, this is going to be idle while this guy is running. This guy's going to be idle while this guy is running. So if process 0 starts to be executing, we're going to save the state into the PCB for process 0. And if process 1 starts, we're going to reload the state. Let's say this one started before this one, it looks like, because this one's already in the PCB. Then we're going to reload the state from the PCB and start running, execute it. Oh, now we're going to save it, put it into the PCB. So we're constantly upgrading and constantly updating the PCB. And so a PCB implemented in the form of a hash table runs faster, because what we need to do is make sure we have a fast lookup. So then that's where your data structures and algorithms course comes into place. So as a computer science major, you take that course so you can figure out how to make this process more efficient, because efficiency is an issue at this point, because you don't want to make, if you're constantly searching something, and this is going to be big depending upon how many processes you have. So as a user, you make this smaller by not running everything you don't need to run and close down programs you're not using. This actually becomes smaller. Some people do notice a significant difference. I don't know. I've never really noticed a difference, but some people do. I guess it depends on how much memory you got. So, process scheduling queues. So here's our queue definition. We have job queues, ready queues, device queues. The job queue is a set of all processes in the system. The ready queue, this is the queues from process perspective. I have CPU queues for different schemes to give you later for different concept, but same kind of works with this concept. The ready queue, set of all processes that are residing in memory, ready and waiting to be executed. And then the device queues, which is a set of all processes waiting for I/O devices. So processes migrate among the various different queues. Do they move? No. Process always stays in memory constantly, same spot. But abstractly, this is an abstraction. Abstractly, it moves between different queues. What's doing that? The state changes. So the state changes are making it go from the ready queue back to the job queue. Well, it doesn't normally go back to the job queue. It usually goes between ready queue and device queues. Because what do we do on our computers? Well, we're using devices. What are the devices? The keyboard, the mouse, the USB port. Everything's a device. So we have different devices. Actually, if you study Unix, everything has device drivers. Everything is even a file is a device, which is kind of interesting. So, and that's one of the hardest concepts to kind of get by, is like the computer abstraction versus the user's perspective. I don't really see the hard disk or my files as devices, but they are. So the ready queue and various I/O queues. We have ready queue over here. This is meant, it says head and tail on here because it's meant to look like a linked list. If you know C++ or C, and you know the concept of a linked list, that's how this thing is implemented. So we load it up into memory and we put pointers in the memory locations to other ones in memory. And we go through the list iteratively by following through the memory locations, which is kind of interesting. If you don't know about linked lists, don't worry about that. Just know that the memory itself is linked together. The queues have a head and a tail to it. We go through each one of the queues like a list. And then we can go from, this is a PCB7, PCB2, PCB3, PCB4. And you're wondering with, perhaps I say, well, we have a PCB. And I usually, the expression have a, like one PCB. Well, the CPU's got a PCB. Every single one of your processes, every single one of your I/O devices might have a PCB as well. So what do we got here? Mag tape 1, disk, terminal. This is like the screen. You see all these different PCBs. So there might be a different process control block for the I/O. Depends on the configuration. So there's no one standard way of doing this. You have different configurations depending upon different goals, different objectives. So representing a representation of the process scheduling. Here's kind of an interesting concept of what we're calling CPU scheduling. So as I mentioned before, everybody gets to visit the CPU at least once. So ready queue, we go to the CPU, then we go down and the CPU says, it's like the traffic guard. So what do you need? I/O request. Oh, okay. Then we get some I/O, and then we go back into the queue. Then we get CPU time again. So every single click takes CPU time, or every single. And what we do is we come up with these different ways of describing, well, how much time? So we have these quantum times, and we have some slicing that might happen, and then we have non-preemptive versus preemptive processes. So we're going to let some things run continuously, and then we're not going to let some other things run that way. Because what you don't want to do is preempt I/O normally. As an example, you're writing something to your DVD disc, your CD-ROM or something, or you're reading something from the CD-ROM. Do you really want to interrupt that so something else can run, and it's going to make it run too slow? So I/O is time consuming, so we don't preempt it. So it gets longer burst time, which is the longest CPU time, which means it's going to make your system run slower because it's hogging the CPU essentially because it needs it. Otherwise it's going to be too time consuming to slice it all up, run it in increments. The thing will never finish actually. And your movie would go like, hello, it would be like jerky, which is funny because if you've ever done this yourself, if you've loaded a DVD on a Windows XP system and a slow processor, it stops and starts and stops and starts and stops and starts. It's because it's not getting enough CPU time. You need a faster processor, more memory, more caching, or set up a caching system for it. Your software, most of the primitive DVD software, the original stuff, had caching systems on it. So it would read it in, it would read there for a few minutes, okay. And then it would start playing it, and it would constantly read into the cache, because it can read into the cache at intervals and not continuously. So you get a streaming effect because you're not reading the disk information, reading the cache that's being created for it. The process actually is still being used, so, which is not bad. So here's our schedulers. As I mentioned before, we have long-term, short-term, and medium-term. Long-term, short-term. What is it? It's just describing when and what we're bound for. So a long-term scheduler or a job scheduler selects which processes should be brought into the ready queue. Everybody's in there. We're all jobs if we're a process. Short-term scheduler selects which process should be executed next and allocates CPU time. So short-term, I always think it's a short wait to go to the CPU. You don't want a long wait to go to the CPU. So if you schedule it out, then you can schedule out different quantum times for each one of the processes depending upon the scheme that you're putting together to design this. So we know that the CPU is going to be shorter, so we're going to spend less amount of time. It's not necessarily the time spent, although it kind of relates to it, but the purpose of the labeling of this as short-term, long-term is necessarily going to be the clock ticks that are going to be assigned and the amount of CPU power that's going to be assigned as well, and for different purposes. And then here's our medium-term scheduler. The medium is kind of the swap in between, and here's the swapping in and the swapping out that I mentioned. So we have a ready queue, and the ready queue goes to the CPU, and the program might end. We're done. We just did a math calculation, or we just used the CPU, but it's kind of rare. Usually we're going to go to the I/O, so then we wait for I/O, we get our I/O, we go back into the ready queue. Or we might go to the CPU, don't go to the I/O, but get swapped out. When we get swapped out, we're partially executed, we're swapped out process, we might end up becoming into a medium queue scheduler, and then we're going to get swapped back in. Why are we going to swap us out and swap us back in? Maybe we're time consuming. Or maybe we're doing something that's slowing everybody else down, which, is kind of hard to predict, actually. So short-term schedulers invoked very frequently. usually in milliseconds. Must be fast. Long-term schedulers invoked very infrequently. Seconds, minutes, maybe slow. So if I have a minimized program, I'm going to put it, it's going to go to the long-term scheduler. We don't want to take it out of memory, we don't take it out of the scheduling system, but we want to store it still. We can't get rid of it, the user still has it out there. Then we move it over to long-term scheduler. So it controls the degree of so long-term scheduler actually controls the degree of multi-programming, because it's the degree of how many windows do you have open. How many of them can be kept track of in a long-term scheduler. So throughout the Windows improvements throughout the years, long-term schedulers have really improved. So we can have things that sit out there. We don't see, if you have a long-term scheduler implemented correctly, you have a bunch of windows up, and this happens actually even today. You have not so much with Windows 7 and 8, but with XP, you have a bunch of windows open. Have you ever noticed sometimes when you go back to something that's been in a long-term scheduler, you probably don't know that, but minimized process, you maximize, you make it bigger again, and then you get waiting, and then sometimes you get, oh, not going to wait any longer. If you do wait long enough, it does fix itself, but most people don't want to wait for it. They just close the window. That means it got swapped out. And now it needs to be swapped back in, and something went wrong with the swap in. Because the scheme is only as good as it can be. You know, there's mistakes, which is natural. So, and it usually happens with the longer processes. If the program has been open for a couple of days and you haven't rebooted your computer, that's highly likely you're going to have that problem, because it was swapped out days ago. The longer the thing runs, the more garbage you got. You know, got processes that are still in memory that you got swapped out, that you left part of it by accident. The CPU schedulers make mistakes because it's compromised. If you check for everything, it's going to run too slowly. If you want to make it fast and you want to make it efficient, it's going to make mistakes, and you just allow those mistakes. It's kind of like deadlock prevention. It's easier just to let it happen and recover from it, or let the user recover from it, kind of thing. So anyway, so interesting things happen with long-term schedulers. Processes can be described as either I/O-bound processes or CPU-bound processes. I mentioned these two terms as well already. I/O-bound processes spend more time doing I/O than computations. Many short-term CPU bursts are needed. Short-term, because they're spending most of their time doing I/O. What does that mean? Like a program that reads music from your disk, from a CD-ROM, it's an I/O-bound process. It's an I/O-bound program, actually. Not going to get as much CPU time, which means the program itself is going to run slower. But what's it doing? It's just getting I/O. So if you've ever tried to run two of those together, like you're trying to read from you get deadlock, you get the program, you can Control-Alt-Delete, reboot your computer at that point, because you're going to have two memory-intensive I/O competing against each other, and it's not going to run. So, it's not going to play well. A CPU-bound process spends most of its time in computations, very, very long CPU bursts. So you're going to give a CPU-bound processor in a short-term scheduler. Actually, it's way up here. So the short-term scheduler, you have CPU-bound processes. You're going to give them very long CPU time, because you want the jobs to get in and get out. You don't want to keep swapping among them. They need a lot of CPU time. They're going to be time-consuming. So you arrange it so they get, more than these guys get. So you never let the I/O-bound processes get CPU time, then you get starvation. You have to give them some time, but they're very short bursts, which is kind of like a way of getting stuff done. It's kind of like how people go through a to-do list. If you think of the concept, if you're a list maker, you got a bunch of items on your list. I like to do the easy ones first. Why wait and do all of the hard ones, which I might not get to because I'm going to procrastinate forever, and then I'm going to do the easier ones later. And no, that's never going to happen. So I check off all the stuff I can check off first. Get rid of this, get rid of this. Oh yeah, I can go to the bank, and I can go to this, and I can go to that, and I can do all this stuff in one trip. And then I get all that stuff done, and then I go procrastinate with the long term, the I/O-bound processes. I procrastinate forever until I have to do it because I have nothing else to do. Or it's holding me up. I can't do can't proceed unless I go get gas. All right, I'll go get gas, or something, So here's that word context switching, as I mentioned before. When CPU switches to another process, the system must save the state of the old process and load the saved state for the new process. So context switching is overhead added to it. So we have the processor that runs at a particular speed. This is why everybody likes to increase the speed of that processor. But from a certain perspective, it can only run as fast as the algorithms that are designed to work with it. But you don't want there to be a bottleneck with that CPU. So faster is better in most cases. So long story short, the time it takes to load something into memory, unload it out of memory, and update to PCB is the context switching. And so it doesn't really matter. You want to minimize context switching at all costs because that's overhead that doesn't lead to anything. It's the time the CPU is taking to go save all this stuff because the CPU takes time for context switching. So if you minimize the number of context switching that you're doing, you're minimizing the number of simultaneous processes that you're running because you're minimizing the amount of switching that you have to do and you're running things more sequentially. So the more multi-programming you do, the more multi-process running you do, the more context switching you do. Which is why if you go to a computer, open up 10 instances of Microsoft Word and 10 PowerPoints and 10 of your email programs, eventually your computer will crash because it will spend so much time context switching that it can't do anything else. They call that thrashing. Read it out of memory, take it out, put it back in, take it out, put it back in, take it out. It's either loading and unloading memory or it's context switching to the point where it is just spending all of its time trying to juggle all of those processes you have started. So now from this point forward, you'll only load what you need to load. Don't load, and then unload it if you don't need it. Because, well, you're never going to run into that problem because you have to load a lot. You'd have to load a lot on that system. Which is why a lot of people like to turn their computers off. Turn your computers off, you start fresh. You got nothing loaded. So notebook computers, if you hibernate it all the time, just make sure you're always running the same programs. Otherwise, you hibernate and then you come back, you hibernate, you come back. You do that about 10 times, keep stuff loaded, keep loading new stuff on top of that. It's better just to turn the thing off and reboot the computer because you're going to have less context switching going on. So time dependent on hardware support. So we have hardware support on tablets actually. We have hardware support on newer or higher grade computer systems that do hardware supported context switching. Why do you want to do it on a hardware perspective? Well, it's not using your memory and it's running faster. So it's one way to optimize it. So context switching time is the overhead. The system does not do any useful work while switching. So why don't you if you have a hardware support for it, nothing runs faster than the hardware itself. You can cache it, store it, and then have the hardware working with you. So process creation, this is what you're doing in the first assignment that you're putting together. You have a parent process that creates a child process, which in turn creates another process, forming a tree of processes. So you have an entire tree of processes, which is called process relationships. Unix, if you take Unix, that's what you study a lot of, is the process of the kernel starting up, which is a process, and then that spawns off another process and another process. And it's looking at the tree in terms of what's being created. In terms of resource sharing, the parent and the child are sharing all of the resources that belong together in that process. So if a parent process creates a child process, it's all in the same memory space. Well, if you have a one-to-one mapping between processes and threads. I'll get to that in a few minutes. So children share a subset of the parent's resources, and the parent and the child share no resources. They have their own resources. So for the execution, the parent and the child execute concurrently, which means only one of them can run at a time. So the parent waits until the child terminates, and then the parent runs. So the lowest level in the tree runs first until it's done running. Only one process is going to run within that process space at any one moment in time, and they're both running concurrently. So one of them's paused, one of them's waiting. So in the concept of that shell that you're creating in the first assignment, you're creating a process, and then inside of that process, you're creating child processes that are running programs, that are running shells. So if you've tried to do this, and if you're actually doing the assignment, I've explained this to a couple people by email, but I'll explain it to the group because maybe you're thinking about this, but you're programming it. You're not writing the essay part of it. You're programming this in C. As soon as you create a process, it's impossible to create a background process. Although the assignment's having you create a background process, you have to fake it. You cannot create a background process from a foreground process because it's in the same process space. So if you create a thread, you fork a process. You use a thread, you fork a process. You've got a foreground process. The only way you can do a background is to put the shell in the background. Then you can get a background process. We have foreground and background processes coming up in the lecture, but let me describe that right now actually. No difference except for background has a lower priority for the CPU scheduler. So Unix, Windows actually has background, but it's minimized. It's not really background. You're minimizing a screen. You're putting it in the background, technically. So it's going to get lower priority, lower processing, which means it's not going to get as much CPU time. CPU is going to focus on the foreground. So the foreground is everything running in front of you. It also gets I/O. So it gets standard input, standard output. A background process also gets I/O. So you have to fake, or you have to redirect the I/O so that the I/O is going to a file or somewhere else. Otherwise, it's going to clutter the user's screen. So a lot of Unix people, they write these batches, or scripts, I should say, and they run this stuff in the background while somebody else is using the computer. Because why waste the computation time of the foreground, use the background for it, and then it gets lower. When the CPU sits idle and it's all done processing the foreground, then it processes the background. So it's a little bit more efficient that way. So if you're creating a foreground process and you fork off another child and it's getting a copy of the parent, it's in the foreground. So if you're going to write that program, you have to fake it. You know, you can use the ampersand, not going in the background. You're creating it from a foreground process. But it wants you to create a background process. So it's a simulation, it's a demonstration. It's not real. So not ever going to work for you. All right, so execution, one thread of execution is going to happen at one moment at a time. So process creation, we have the address space, which is basically all we get. So the child duplicate of a parent, and the child has a program loaded into it. So we're a process. We're a memory abstraction. We create another process. All we get is the memory subaddress that's inside of us that tells us where we're at. So we can kill it. We can get rid of it. So the process never knows about its parent's address. The parent only knows about the child's address. So the process ID that's returned from the child to the parent when we fork a process is nothing more than, here we are, we're right here. So if we want to kill you, we can kill you. So parents can kill the children. So if a child is created from a parent and the parent goes away, it can never be killed. There's no way of killing it. You can only kill from a parent to a child. When I say kill, I mean terminate the process. It sounds a bit more dramatic when you say kill. So if a parent dies, we have an orphan. Orphan processes are out there taking up CPU time, taking up memory, and they're sitting out there. Hopefully they're doing something productive. If they're not doing something productive, reboot the system because it's taking up resources we don't need. We have daemon processes that run out there and they cannot be killed. And they don't belong, they don't have a parent. There's no parent that owns them. They're a background process that's just running that nobody is ever going to be able to touch, usually started by the kernel. So it doesn't belong to a parent. And then we have parents that create children. The children run indefinitely. And then the parent's sticking around. Well, that's taking up resources too. So it depends on how you're going to run your multi-threaded program in terms of how you're going to design the concept. So things that run as daemons are print processes. A print queue would run as a daemon, a scanner, an IP address checker, a DHCP assigner, port sniffers, tons of daemon processes that go out there. they're not deemed in bad sense. It's just that they're protected. They can't ever be removed. So they're just out there. We don't see them out there. We can't get to them. So Unix examples here, we have fork. As I mentioned before, fork is the system call that creates the new process. exec is the system call used after a fork to replace the process memory with a new process, a new program. So you can use fork, and then you can use fork again, you can use fork again, you can use fork again, as many times as you want, actually. There's no limit on the number of child processes that you can make. And a child becomes a parent when it creates another child, and so forth. So you have that stream of execution, but only at one point is anyone going to run. So if you know you're going to run, and you're going to just run, and you're going to clean up easily, why allocate the resources for it? And why copy everything? So if you don't want a copy of the parent into the child space, then you run an exec. An exec command says, okay, we're just going to run a program, then we're going to terminate. So it cleans itself up. So an exec is sort of like a lightweight process. You run an exec, and this is a function call, by the way, and so is fork in C. And then you run an exec, you say, hey, run ls. It runs ls. When it's done, it automatically returns back to the parent. So it's a faster way of running programs if you're going to run a process that's going to run a program. If the process isn't going to hang around forever. If the process is going to hang around forever, create it as a process, use fork. So we used fork. We've been doing a process creation in this case. So fork creates a parent, and the parent waits, or the parent waits, excuse me, because fork is the process that created, the parent is using the fork to create it. And then we resume when the child's done. So the child gets created, and then the child is going to run an exec, which executes some command, and then it exit, and it goes back to the parent, says parent, okay, keep running. So it wakes up the parent. So we have signals that get sent back and forth between the processes. And a Unix system actually has a system call interface for that. So you can signal with mutexes to have somebody wait, have somebody not to wait. The automatic behavior of a fork automatically holds the parent. We don't have to tell the parent to wait. It will automatically, the parent will always wait if a child has been created. And then the child's going to do something, hopefully, and then return back to the parent, theoretically. You could create a parent that creates a child and then delete, kill the parent, and then have a child that knows to kill itself further down the road, which is like delayed execution of things. Or, you know, it's a bit different way of scheduling it. Why do you want to do this? Because eventually we want to maximize the CPU power and minimize the number of processes and create a system that runs efficiently. Yeah. So I guess the solution of this would be, you know, just get faster processors and get a lot of memory and not have to worry about any of this stuff. You cannot program in threads or processes on a Windows system. It's called a protected operating system. You can't create threads. On Unix, you can. So if you're trying to do that first assignment and you're trying to do it on a Windows system, not going to work. You can use Java, however, and Java will allow you to create a thread. Java does thread programming. Why? Because it's working on a JVM. It's on its own virtual machine, not Windows. It's not using the Windows runtime. It's not using the Windows interface. So CPU program forking. And actually, one more comment on that. Only way to run a process on Windows is to execute the program. You can't run a process outside of the execution. So, which is actually kind of, it's protective in nature, and it's actually kind of good. It makes the operating system more stable. So you might say you could make a Linux system unstable easily by messing up your process creation. So here's a program here, and this is a C program forking a separate process. You can use this, as I mentioned before, or if you get a PDF or a copy of the book. In the book, there's a shell, actually. This is kind of like a shell, actually. So what do we have here? We have a main program. Don't worry if you don't know the C programming. We're going to create a process ID, which is what PID stands for. We're going to fork a process, so the process ID is going to be equal to a fork command, which is going to return the ID. If it's larger than 0, we add an error. Otherwise, if else print out fork failed, or excuse me, print out fork failed. Else if it's equal to 0, which means it came back successful, then run the exec command, and we're going to run ls in this case. Else the parent process is running. Parent will wait for the child to complete before it actually starts running again, so we're putting in a wait here. Now, depending upon the library that you're using, might not have a, most of them have a fork, but you might have different commands here on exec, lp, lx, ly. There's different variations of this. Use the man pages or the internet to know the different variations. Some of them take different numbers of parameters, essentially. Because this is functions, not objects, so we don't have polymorphic functions. So we have to create a different function with a different function name for each one of the sets of parameters that we're going to call for it. So here's our tree of processes of a typical Solaris system, where we have the scheduler as process ID 0. So Unix, well, Solaris is Unix, Linux and Unix all have a process scheme to them, so there's an ordering. All you have to do is type in PS and you'll see processes. In fact, I can do that on my MacBook here. I type in PS and see a list of processes. And I see one here, and it says PID, process ID. I have 931, which is at just the shell. But I'm getting it from my shell point of view. So if I run another process, stick it in the background, like ls ampersand, as an example, it ran it, and it was like, and it ran it as 936. So it's still it's not running, and it is done. So it says it's done, and the program that ran was ls, because I have the command over here too. So long story short, I'm going to control C it. Oops, I option C it. Oh well, just leave that alone. Long story short, there's a hierarchy to it, and no numbers are reused. So you saw that went up from 9 something to 936, so it increases with each time. You can't predict what number you're going to get. It's automatically assigned by the kernel. The user mode on my system, I believe, starts at 900, and everything past 900 is something associated with something I'm doing. Every time I run a program, like this is preview, that's got a process ID to it. But I can't get it because I was in a shell. So a shell actually forks a process. It's your shell that you're writing, forking a process, actually. Even though I ran it in a terminal. Terminal's forking a process. So. Alright, so we have the login, daemons. We have a whole set of processes that are associated with kernel level processes that have kernel level stuff to it. We actually have a kill command that kills processes. We can process, if the process executes the last statement and asks the operating system to exit or delete it, which is the exit. So we have the exit written inside of a program. There's a system call that says end me, terminate me. So exit inside of the process exits itself, terminates itself. The word kill is not on the slide set yet, but it's a Unix command, which is why it's not a bad idea to take a Unix class, because then you get familiar with the common Unix commands. Kill is the same thing as an exit, but it's done outside of the process, essentially. Wait, you can actually issue a wait, output from the data from a parent to a child via a wait. If you wait, if the child waits, then the parent can run. Hard to figure that out, but usually the parent's going to wait for the child, and then the parent's going to resume. But then you can share information back and forth because they're both working in the same process space. Processes resources are deallocated by the operating system when a wait occurs. So the parent may terminate the execution of a child process or abort it, and the child has exceeded the allocated resources perhaps that it was allowed in some cases, then that might happen. Or the tasks assigned to the child are no longer required. We can get rid of it. If the parent is exiting, some operating systems do not allow a child to continue if the parent terminates. Windows does this automatically. When you load up Word, as an example, it's loading up one process, and you might actually go into Task Manager and see you've got Word in there several times. Because it doesn't know all the sub-processes that are associated with the main process, so it's labeling it all the same. Well, you get rid of one, usually you get rid of all of them. You're supposed to get rid of all of them. Problem is sometimes you get rid of one, but the rest of them are still there, so you double-click and it still thinks it's open. So you got problems. So child terminated, we have cascading termination. in most cases. That's called cascading termination, and all the other sub-processes go away as well. Cooperating processes. So one of the things that we'll look at in this class as well is inter-process communication, IPC, with all of the different scenarios of the dining philosophers and the readers and the writers and the bankers' algorithms and stuff, which gets into the concept of how do we make them cooperate. We have independent. So independent processes or process cannot affect or be affected by the execution of another process. So it's independent of itself, and it runs on an island of its own. And then we have cooperating processes that can affect or affected by the execution of another process. So we can run another process that affects our process, essentially. Advantages of process cooperation. Well, then what about information sharing? It's kind of like if one person's going to do a job, or you're going to get 5 people to do a job. If 5 people are doing the same job, then they should probably divide the list out or divide the tasks out, and each one of them do like a different one instead of everybody doing the same thing. So delegate the work out. So that's a process of cooperation. So we can we need to share information between the processes. We have computational speed up, obviously, modularity, convenience. So it'd be nice to have, like, tons of people working on something. So, which is the classic CP command, or a copy command. Actually, it's 2 processes running for that. We have a producer and a consumer. So the producer and the consumer is, well, someone's going to read something and somebody else is going to write something. Because if you're going to have multiple processes running together in a cooperative environment to fulfill a task like copying a file from one location to another, you can easily break that out and just do separate processes. And then you're going to have one of them read all the stuff into memory and the other one write it all out. So which is where we get the producer-consumer problem. So paradigm of cooperating processes, the producer produces something, takes and reads a file, puts it up into memory, and then it's consumed by the consumer process that takes the memory and writes it back out to the file, to another file, because you're copying it from one location to another. You're never going to move it, you're going to buffer it, so you'll have some memory that you're going to share. So we have this thing called a buffer, which is the memory that's being shared between the 2 processes. Think of it as memory space. So we have 2 components of it. We can have a bounded buffer or an unbounded buffer. Are you going to put a size limit to one, or are you going to not make it unlimited? If you're going to have well, for practical reasons, if you're going to limit the amount of memory space that's associated with a process, you're going to have it bounded. So it's going to have a size to it. Unbounded buffer places no practical limit on the size of the buffer. Could be dangerous. Actually, if you're copying, if you go into Windows Manager, File Manager, you might notice if you copy like an entire folder, it doesn't really matter how much folder you copy or move or drag or do whatever, it'll just do it. But sometimes it takes longer than others. It's unbounded. It doesn't. You can actually take an entire hard disk and move it to another one. In that particular case, if you bound it, it'd be kind of ridiculous from a user's perspective. If you can't move this, can't move that, no memory. Sometimes you actually get, when you cut and paste in Windows, you get messages when you leave programs. Would you like to leave the memory? We copied something up in the memory, and it's taking up a lot of room. Would you like to leave it? No, which is new, actually. It never used to happen. So, unbounded buffer assumes that there's a fixed size buffer. The CP command is going to do an unbounded buffer so it can efficiently read, write, read, write, read, write. So does that mean it has to read everything up into memory and then write it all back out? Well, I have 2 processes. So if you can take turns back and forth, then you can read part of it, write part of it, read part of it, write part of it, and they can both sort of be working simultaneously. It means the work's cut out into 2 phases, and the 2 phases are running one after the other intermittently, but not necessarily read it all up, write it all out, because you can have one process do that. But if you have 2 of them doing it, it's more efficient. So the bounded buffer using shared memory solution. So this is actually what I've been describing. You have a piece of shared memory that and it's bounded, certain size, which means we're just going to set a size limit to this memory. It's not going to consume everything on the computer. And it's shared because both processes are able to read and write to it. Or one of them is doing a reading to it, the other one's doing a writing to it. The pseudocode sort of looks like this for the shared memory, where where we got type define here where the structure is going on. I mean, the structure, we're gonna have a buffered item here, which is the structure, and the item is gonna have a buffer size associated with it. We're gonna have a integer for the in and out. We're gonna keep track of how many we've written to it and how many we've read from it. And what does this say? The solution is correct, but can only use buffer size of -1 elements. Well, it depends on how you're configuring it. You want to make sure that you're reading more than you're writing, or writing, excuse me, yeah. Writing to the memory and then reading from the memory. You're not reading an empty piece of memory or writing to something that's full kind of thing. So it does take some coordination. Using memory to share between processes can be time consuming as a solution to process synchronization and process sharing. The faster way of doing it would be to use the kernel support for it, semaphores and mutexes, where you're signaling back and forth to one process. So we have two forms of inter-process communications called direct and shared memory, or indirect, direct, where one process is talking to the other one, saying, okay, read, okay, write. And then instead of looking at a piece of shared memory, and the shared memory is does it have stuff in here? Does it not have stuff in here? So there's different configurations, and we have an entire chapter on process synchronization. This is just an introduction to it. So the process chapter, which is chapter 3 that I'm lecturing on today, has so many different concepts in it that are related to so many other things of the operating system. So it's hard just to talk about processes without getting into CPU scheduling and memory management and shared buffers. So you don't, bounded buffer here is for an insert command, removal command. I'm not going to go through the source code, but because I'll do this in a lot more detail as we go through that chapter later on. So inter-process communication, and by definition, as I mentioned before, IPC, it's short for IPC. The mechanism here, where we have a process for communicating and synchronizing actions between multiple processes. We can have a message system, kind of like a mailbox system, where the processes communicate with each other and without resorting to shared variables. So if I sent you a message and said, hey, and then you got to read your message, or I sent you a signal, then I could communicate with you without you having to do anything. IPC facility provides two operations of send and receive. This you need kernel support for. This is not supported actually on a Windows system. It is supported on a Unix system, because Unix system has it built in to the system call interface. So if we don't have this as part of the kernel, why are we going to allow the user to create processes? We aren't, which is kind of sort of why Windows systems don't have process control from a user perspective. There's no way of controlling it. It would be very unsafe for a user to create a process on a Windows system. Nothing from the kernel level is going to support it. Alright, so then we have if P and Q wish to communicate, they need to establish a communication link between them, exchange messages back and forth with send and receive. So the implementation of the communication link can be physical or logical. Physical with shared memory, or logical with logical properties. So we have some implementation questions, and let's see how far we can get through this here. I think I'm going to go through all the way up to synchronization today. So let's see, I'm finding a good stopping point for today, because I don't want to leave you half in the middle of this topic. So, and I'm looking at the time going, Implementation questions. How are the links are going to be? Okay, so now I'm getting into the concept of inter-process communication, and how are we going to establish the communication between these so we can get this between processes. So how are the links going to be established? Are we going to use messages, or are we going to use shared memory, stuff like that? How can the link be associated with more than one process, and should it? In Linux Unix, you can have any number of processes communicating, multi-process linking. And just remember, in Windows, you have nothing. You can't do this. What's the capacity of the link? Is the size of the message that the link can accommodate fixed or variable, bound or unbound? And is the link unidirectional or bidirectional? Can you talk back and forth, or can you only send and can you only receive? So here's some communication models here, where we have process A And process B, where we have A and B are just two different models where we have shared memory. Process A looks at the memory, process B looks at the memory. We read and write to a piece of memory. Or here, we're sending messages back and forth. And we're opening up our process space. And we're saying, okay, what's my mutex? Or what's my number? And we're checking a value, or we're checking information. And we're allowed to actually enter into each other's process space. Not very protective. One process could actually change something about another process. Very protective, but slow. Now we have shared information that's running in between the processes. And this is a memory abstraction, by the way, again. So this one's going directly in. This is the direct approach, going directly in, talking to the kernel, and having the kernel support it, which is different than this one over here, where there's no kernel support. You can mimic this in Java. You can't do this in Java. The kernel, actually you can. There's this keyword called synchronize. Synchronize. You can synchronize a method, class, and you can have the kernel manage it for you. Synchronize means that the kernel is not going to let more than one process run at the same time. When we get into process issues, there's two major issues that we're trying to avoid, which is why we're thinking about all these scenarios. If we have multiple running processes, we're going to get deadlock or starvation, which are the two, running two issues. So the deadlock is when two processes are going for the same resource simultaneously and neither one of them is getting it. Or the starvation is one process is using a resource constantly and not allowing the other one to use it. So the other one is never going to get a chance to finish. So if we facilitate better communication between all these processes, then we end up with a situation where we don't have deadlock and we don't have starvation, which is why we talk about interprocess communication in an operating systems course. It's because we don't want the operating system to deadlock. We get blue screen of death. The whole system goes. Or we don't want starvation where you can't ever run a program. Everything else is running and you can't run your window, you can't run your web browser or something. So we don't want those two scenarios. So the process must name each other explicitly on the send and receive if we're going to use a direct communication method. So remember I said before we have direct and we have shared memory solutions. Direct or indirect. And so properties of the communication link, the link is establishes automatically with a direct, and this is controlled by the kernel. This is direct over here. So, and the link is associated with exactly one pair of communicating processes. We have two processes that are communicating. Each pair, there exists exactly one link between the pairs. You can't have multiple links, otherwise it gets too confusing. And the links are unidirectional, but it's usually bidirectional. But it's usually bidirectional, but maybe one way or both ways. I can never say that word. So, typically, they're bidirectional links by default. You can make it unidirectional. So, that was for a direct model. For an indirect communication, we're using a message box. So if I came out, think of it as like human communication. If I came over to you and said, "Hi, how are you?" I'm directly communicating with you. If I write you an email message or a text message, later on, after the class ends, 15 minutes from now, you're going to, oh, look, I got a text message from the teacher. Say, hey, it says, hi, how are you? That's indirect. It's a mailbox. So using a text message and email message, you can indirectly communicate with somebody, which is kind of funny because most people have resorted to indirect communication in every part of their life. It's like, why don't you just talk to the person? You see kids at dinner tables, they're text messaging back and forth. It's like, this person's sitting in front of you. Why don't you just talk to that person? Well, maybe because they're not allowed to, so they're indirectly communicating. All right, so messages are directed and received from mailboxes, also referred to as ports. So each mailbox has a unique ID. Processes can communicate only with the shared mailbox, so which is like, your unique ID would be your telephone number. And in this particular case, the only way I can communicate with you is to send you a text message to that telephone number, and you'd get it there. Properties of the communication link here. The link is established only if the processes share a common mailbox. If I don't know your mailbox, I can't talk to you. So, actually, this is two common mailboxes. You can make it so it's one, which is what this is talking about. So if we both had the same email address, we could both write to it. It's kind of like a Google Doc, actually. Google Doc works that way, where you're sharing. It's actually kind of interesting because it's a mailbox, but it's a link. and it's a document all in one, which is actually kind of an interesting concept. So a link may be associated with many different processes. Many different people might be using that mailbox. And each pair of processes may share several different communication links. You can have everybody else's telephone number as well. It doesn't have to be just one person. And the link might be unidirectional or bidirectional. So we can have two people logging in or logging out. I guess chat systems would be more of a shared, because two people are reading to the same chat screen and writing to the same chat screen. So chat system also represents that as well. In the indirect communication, the operation might be to create a new mailbox, send and receive messages to the mailbox, destroy the mailbox. And we have primitives for that are supported by the kernel to send and receive. And we have mailbox sharing techniques. So in terms of mailbox sharing, how you're going to get past the problems of who's receiving which message when and who gets the message. It's kind of like our postal service where we put direct, zip codes that are matched correctly and the address and the name and everything. Solution is to allow a link to be associated with at most two processes, limit the number of processes, and we can tell who we're talking to. Allow one process at a time to execute or receive an operation. That's another solution. Or allow the system to select arbitrary receivers, and the receiver is notified by who the receiver was or so. Alright, this is where I said I'd stop. So TA, try and remember, I am on slide 35. And I'm going to talk about synchronization, because what we're going to get into is blocking and non-blocking processes, and synchronizing, which it goes into a bunch of different scenarios that I don't want to start the topic and then like end it in the middle. I'll start it fresh next time. Questions, comments, concerns? Are we ready for lunch? I'm ready for lunch. Then let's have lunch. Oh, but make sure to sign the attendance. So if you're in the class and you are here, let me stop this video. Okay, everybody, let's get started. Today we are going to finish lecture number 3 and starting with lecture number 4. Lecture number 3 is on threads, and it's on processes. Lecture number 4 is on threads. So today we'll really see the concept of threads and processes being brought together, hopefully in some sort of an abstraction that makes it clear in terms of what we're looking at. For those of you who weren't here last time, what we started with was this lecture. It's always weird when I start in the middle of a lecture. So I want to review the concept a little bit in terms of what it is we're talking about, and then start fresh where I left off. I was talking about processes in terms of what's happening, and that's really the abstraction the user has on the computer. When you're running your operating system, you're seeing everything in the form of a process, is what I mentioned before. And every program that you're running is running in the form of a process. So we have this concept of the scheduling of these running programs, and we have the cooperation between the running programs and the communication that might go on. And then we have the looking at the different platforms for how processes work, and that's where we get client server and distributed computing. Because if you think about it, if you can take processes and distribute them over many different computers, then we've really established what's called a distributed computing environment. And if we have some processes that run on a server and some processes that run on a client, and we have them communicating back and forth, we have a client server. So a lot of the networking technologies and a lot of the concepts associated with networking are all process-based, which is kind of interesting. And when you talk about processes, you're really talking about operating systems concepts as a core. So that's why I like to spend a lot of time on processes in this class, because it really is a basis for what we're doing. We're creating a process abstraction when we create the user interface, where we have multiple versions of different processes running. We might have, in fact, on my computer right now, I've got a preview running. That's a process. I might have an email program running in the background. That's another process, et cetera, and so forth. So I talked about what process was, and I mentioned that it's a memory abstraction. And here's what it kind of looks like. And we have multiple parts of a process. The reason why I'm reviewing this is I'm giving you some hints in terms of what you want to see on the final exam and what you'll see on the take-home midterm. And so kind of the learning objective here. You want to know what a process is, and by definition, it's a running program. So any program that's running in memory is a process. There's many different definitions of it. The book calls it jobs and processes. A job is a process, per se. We'll talk about threads later on today, and you'll see how that differs from a process as well. The process in memory is nothing more than an abstraction of memory. So we have the memory that's broken out into different parts. We have a stack, we have a queue. We don't have a queue. We have a stack, we have a heap. That's what I meant to say. We have data, we have text. So we can keep track of the running information of the process. What we don't want to do is keep reading and writing to a hard disk. Instead, we want to load all this stuff. The process is really that executable, that's exe file loaded up into memory. When we double click on that file, we load it up into memory. It looks like this in memory. And so down here is the data and the text. Well, the text is pretty much the running instructions, and then it gets loaded on the stack. And then the stack might create some dynamically allocated memory on the heap. And we're using this process space to run the process, essentially, and to organize what's going on with it. When the process is done running, it goes out of memory. So this stops, and it terminates at the end. So it's kind of interesting in terms of the abstraction. And this is also sometimes referred to as the runtime environment. So the runtime environment is the process stored in memory and the running of the filling up the stack, emptying out the stack, filling up the heap, removing items from the heap, and going back and forth. And that works with CPU scheduling, as I mentioned last week, and a couple of other concepts as well. So the processes have many different states associated with their lifetime. When a process starts up, it is new. It just starts, and it's not really running, it's just new. When it actually has some instructions executed, then it turns into the running state. And then it could be waiting at any one moment of time, so the process is waiting for some event to occur. It may also, when it's not waiting, it might be ready. Instead of going back into a new state, it pretty much goes from new to ready again. And ready says that it's waiting for it's waiting to be assigned to a process, or it's waiting to have something happen to it. And then it could be terminated at any point. So, and then we have Unix system calls that create processes and kill processes. In fact, to terminate a process, you just type in kill. To start a process, it's usually in the form of a thread. So it's a P thread or a thread, depending upon what library you're using. And then you go ahead and start a process. So that first assignment is really on this concept, the one that you're doing the shell for. So, and I know a lot of you guys are working on it, which is fantastic, because you don't want to wait till the very last week of the class to turn everything in. And it's better to do it earlier, actually, especially because this is the summertime. The last week of class, you'll be enjoying the last couple weeks of summer. You don't want to be like doing this stuff. Plus, the first assignment is also the hardest. So when you get past the first one, the rest of it's a piece of cake, actually. So some people will probably just wait till last to do the first assignment, but it's okay. All right, so here is the running process and a diagram of the process state. So we have new, and then it gets admitted into a ready queue. The ready queue comes back and says, well, from the ready queue. And think of these as queues if you want to. We have a whole new queue, we have a ready queue, a running queue, a waiting queue. In fact, when we start looking at CPU scheduling, which is probably not going to be till next week or the following week, you'll see how the queue abstraction is used for the processes, and processes just spend most of their life in different queues, waiting to get stuff done. And then usually the big old question comes into play, says, well, why so many queues? Why do we have to do this to it? Because we want multiple processes to run simultaneously. So in a multiple-threaded, multiple-process system, we have to set up some elaborate scheme to get all this stuff to work simultaneously. Otherwise, we just have batch processing, where one process runs, it stops. One process runs, it stops. One runs, it stops. So it doesn't give us the same user experience. Is there anything wrong with that? No, in fact, that runs faster. It runs much faster than having to do all this stuff, because what we really want to do is just run the process, right? So that's why more processor power and more processors on the system, it makes your system run faster. Think about it. So all the information about the processes are stored in what's called a process control block. A process control block is held by the kernel and the kernel memory, because remember from lecture 1 we have user mode, kernel mode. Kernel mode has the memories associated with it. And again, this is another abstraction. User mode is memory spaces above a certain level. Kernel is just memory below a certain level. When you start up, we don't want to keep reading and writing to a disk. Instead, we just load everything up into memory, and then we read and write from the memory, which is kind of interesting. In fact, of all of operating systems concepts, I think memory management is the most interesting in terms of how in the world did someone invent this scheme of doing stuff this way. So process control block held by the kernel stores the information about each one of the processes. It might hold the state. The program counter, what instructions did it leave off, which is the next instruction, the CPU register, CPU scheduling information, memory management information, accounting, I/O status, and stuff like that. So again, it's another piece of memory that's being held for each one of the processes. So here's a kind of an example. If you were to actually see a process control block, it would sort of look like that, kind of, sort of. None of this stuff really has pictures to it. They're all concepts. I also talked about and introduced the concept of CPU scheduling last week, and CPU scheduling switches from one process to another, and here we have two processes running, process 0 and process 1, and then we go back and forth by saving states, reloading states, saving a state, reloading a state, in order to achieve that multi-programming that we're interested in seeing. So, now this is going to be slow compared to just running one process, running a second one, running a third one, sequential processing, but unless you want to go back to the DOS days, Windows is going to require something a little bit more elaborate. In fact, most of your desktop experiences are facilitated by multiple processes running in a pseudo-simultaneous kind of form. So process scheduling has different queues associated with it. As I mentioned before, scheduling is all about those queues. Process is all about living in queues. So we have the job queue as an example, which is a set of all processes in the system. They call them jobs because you're going to call it a process queue? Well, they're all process queues. So this is going to be the job queue. And then we have the ready queue, which is all the ones that are ready to run. And they're in memory, they're waiting, they just need to run. And we have device queues. So we separate out the CPU processing from the device processing. Then we can, kind of intelligently schedule things a little bit more efficiently. If everything were waiting in the same queue, we would be waiting a very long time for the CPU or a very long time for the I/O. Bottom line, I/O takes longer. So if you're having a process come into the queue, you're going to separate it out, put it into a device queue. Say this is waiting for the CD-ROM drive, this is waiting for the disk, this is waiting for something else. Because if it sits there waiting for the CPU, which everybody has to have CPU time in order to run anyway, then you've got a big, long, huge CPU queue. So then they have this concept of short-term and long-term and medium-term queues, where this kind of fits into place. So we're going to have a job queue, we're going to have a ready queue. Now these device queues, they can be separated out into different lengths, and that slide's not coming up for a few more, but if we have short-term, those are CPU-bound processes. They're getting in short bursts of a CPU. They don't need too much of the CPU time. If we've got a long-term, they're waiting for I/O, essentially. They're waiting for the I/O device to become available. And as I mentioned last week as well, it's not only the time that the process is waiting in the queue, but the nature and how many bursts is it getting. So we measure quantums or bursts is the measurement associated with time. This time is associated with how much time are we going to allocate for this process to use this device, this process to use the CPU, etc. and so forth. So you'll see a bunch of different terminology used. I like to use bursts, CPU bursts, instead of quantums. Quantums, 2 quantums, 3 quantums. Some people use the two terms intermixed as the same thing. There really are supposed to be two separate terms, and they do mean two separate things, and I'll get to that when we start talking about CPU scheduling. So here's an example of the ready queue and various different I/O device queues. The ready queue has here's a ready queue here, has a head and a tail. And for those people who are familiar with linked lists, you might wonder, well, isn't that kind of like a linked list? Isn't it? Yeah, it is very similar to a linked list. A lot of the queues themselves are going to be stored in a linked list. It's easier for putting something in, moving something around. It's a rotating circular queue. So in terms of the abstraction, it lends itself, and we're working with memory. So why not have that memory just point to another memory, point to another memory, point to another memory. So we have a head and a tail in this queue, a head and a tail, a head and a tail. And this might be for different queues for different purposes. That says mag for mag tape, so disk, terminal. I don't think we have any mag tapes anymore, but kind of brings back memories like tape drives. So we have CD-ROMs now, and big old SD cards now, no tape drives. So tape drives had their place in time though. And you may also notice here we have multiple PCBs, process control blocks. This is a multiple PCB configuration. Usually somebody in the beginning kind of wonders about it and says, well, how many of these do we have? You can actually have as many PCBs as the configuration, in the configuration, as what would make sense. For example, you can have a process control block for all processes. And then inside the process control block, you can have a sub PCB and then another sub PCB inside of that. So if you can layer them or nest them together, then you can really keep track of everything. What you don't want to do is have, like the old days, have a single PCB that runs everything, because then the queue gets kind of big. And if the queue's big, you got it, the sorting and the searching through it takes a longer time, bigger search space. So if you can pinpoint what you're looking for, exactly where you're looking for it, and only have a couple of items to kind of scroll through, process is much faster. So when you study operating systems and you start building your own operating system, that's when you start taking advantage of your algorithms and data structures classes, because then you can build heaps and you can build trees, so you know the data structures and then the algorithms for which kind of sort's going to work for efficiency purposes, and what kind of search are you going to try and do, and how you're going to optimize the data structure to work with the search a little bit more efficiently. And so that's when it comes together, essentially. Here's the presentation of the process scheduling. So we have a ready queue up here. In the ready queue, everybody goes to the CPU. And then we come back down and we go into, maybe we have an I/O request, or maybe we have a fork a child, or maybe we're going to wait for an interrupt, and then we're going to come back, and the interrupt's actually going to occur, then we're going to come back up, and we're going to be in the ready queue again. So processes do a lot of waiting, actually. They do a lot of sitting around and waiting for stuff. The wait time of a CPU scheduler determines its efficiency. So when we're going to get to CPU scheduling, we have an assignment to do that is a simulation of a CPU scheduler, and you'll start seeing how the pieces will come in together. Depending upon what algorithm you choose for the scheduler, the wait times might vary. So it's kind of interesting how that works. And schedulers, here we go. We have the long term and the short term. Long term is everybody, it's the job scheduler. CPU is short term. It's only brought into memory for CPU time. It selects each process and then allocates the CPU to the next one. So it works efficiently that way. We also have this concept of the addition of the medium term scheduler. Well, medium sits in between short and long, doesn't it? So we have partially swapped out stuff. We just put one in between as a kind of a catch-all for the parts that are in between. So if it's not in the short, it's not in the long, it might flop back and forth. It makes it so it's a shorter jump, especially if the short term is kind of time consuming. We can put some stuff in the medium, delay it, prioritize it, and then, because we have priority to think about as well. Most of your kernel level processes get higher level priority than your user mode processes, because if it weren't for the kernel, the user's not going to run, the user mode's not going to run correctly. So we need to make sure all the kernel level stuff gets run. So we talk about the schedulers. We have the short-term scheduler. It's invoked very frequently. It's in milliseconds. It has to be fast, because if we have a short-term scheduler that's slow, the entire computer is going to run slow. This is what gives us our user experience. This is what gives us how fast things run. It doesn't really matter how much memory we have on it. If we have a really bad scheduler, we have a really slow computer. So, long-term scheduler is invoked very infrequently. Might be slow. It's not going to get, probably will end up with a longer time as well, because it needs more resources. And the long-term scheduler controls the degree of multi-programming, which means how many processes can we have running simultaneously. So we can describe processes as being I/O bound and also CPU bound, as I mentioned before. So I/O bound is waiting for some I/O. Well, but you think about it in a nutshell, what do we use our computers for? Mostly I/O. We're mostly, moving a mouse, typing on a keyboard, accepting a command from somewhere, responding to interrupts and stuff like that, which is all input-output, when you think about it. So it spends more time doing computations, very few long CPU bursts, if we're an I/O-bound process versus a CPU-bound process. The CPU is going to spend more time with longer CPU bursts, less I/O time, and vice versa for the I/O. I also mentioned the concept of context switching in the last lecture, and context switching is nothing more than running one process, saving its state, updating the PCB, and then running another process. So we have one process running, then another process, and another process. Saving the state, loading one up, unloading in the other one, context switching. So the system does no useful work when switching. The higher level of context switching is the slower running computer. So the more context switching you're doing, the slower your computer's running. And I think I brought up an example last time with, just load up like 5 different versions of Microsoft Word or 12 different versions and only use one of them. It'll run slower than if you have just one of them loaded. So long story short, close down those programs you're not using. It's a higher level of context switching because the process is still out there. If the process is still out there, it's not going to get garbage collected because you're still using it. It still has an entry into the PCB. It's still running. So every once in a while, it's still got to check. Are you still running? You say, okay, we're minimized. Okay, keep going, keep going. It's still checking. It's basically using CPU power, even though it's minimized, which is kind of ironic, actually. So it all starts with the process creation, and then so we have a parent process that creates a child process, and we have resource sharing. In most modern day configurations, the parent and the child share the same memory address, and the parent-child gets a copy of the parent's memory address, but they're all located at the same spot because they're all sub-processed and they're all in the same hierarchy, so they're all running together in the same memory location. But they could keep separate memory amongst themselves. So the child gets a copy, and then the child can change it around, and then in the end it goes back to the parent. In terms of the execution, the parent and the child execute concurrently. Usually one of them is running at a time. So the parent will wait for the child to terminate, then the parent will start running again. So in the process creation, we have the address space that is being used as the abstraction, and the child duplicate of the parent, and then the child has a program loaded into it, into the terms of the child. And then on the Unix examples, we have fork and exec. So this is really going back to that first assignment that I've been talking about. So the process creation, if we were to look at a diagram of it, so it kind of looks like this. Yeah. Does it really look like this? I don't know. So this is somebody's abstraction of it. And when we use the fork, and this is a system call, by the way, we have a parent waits and the child runs. So this is what you're programming in that first assignment when you're creating the shell. So until you actually kind of work with it, it's hard to sort of see it work, which is why I put together an assignment for you on that. So here's the C program that forks a separate child process. If you're not familiar with C, then you're doing the alternative form of this and writing pseudocode, or you're putting a lot of notes in here to make up for what you don't understand in terms of the programming component. And the idea is not necessarily to get a perfectly running, compilable, running program in C, especially if your background's in healthcare or something and you're not a programmer. It's going to be impossible for you to write this. Learn an entire C language and program in threads all in one assignment. Not necessarily what I'm asking for. But if you are familiar with C, and if you are a computer science major or software engineering major, I highly recommend learning C. In fact, I think I'm teaching C. So I'm teaching C++ in a weekend course. So maybe some of you are in that class. Anyway, if you are familiar with C, we have integer main going on here in a main program. It's not object-oriented, it's procedural. We're going to fork. This is a process. When we run the program, it turns into a process, so our process is forking another process. So our running program is main, and our running program is the main process, or the parent process. When we fork, we create another process. We're waiting while this forked process is actually running, and then we can check for an error, and if not, then we're going to run an exec in this particular case, and this is an LP, exec LP. When you write that program, you're going to see WP, LP, PP, all these different switches. It's because this is a procedural, not an object-oriented program. We have different function calls for different versions of this. What are all those different versions telling you is how many arguments and what order are the arguments coming in. Because what we're doing is running exec, which just essentially says execute, short for execute. What does execute do? Well, in the child process, it's going to run a program. In this particular case, it's going to run ls. So this is actually, if you're going to write that program for assignment number 1, this is a good base, actually. Compile this, see if it runs, actually. So And if you are going to do this, you want to install Linux or get a startup disk. I investigated the Amazon servers, and it's great. However, it's all cloud-based stuff, and there's no C in there. Not going to help you, actually. There's no GCC compiler on that you can use. It's actually more for web programming than anything else. So what I would highly recommend is doing a Google search, downloading one of these disks, ISO files for Red Hat or for Debian or any version of Linux. You burn the disk, the DVD or the CD, you stick it in the computer, you reboot the computer, it boots to the live disk. It's a live Linux disk, and that gives you a live Unix system on your computer. And then put in a USB drive. Everyone's got them nowadays, little thumb drive. Save your work to the USB drive. So you can even write it in Windows as an example using Notepad. Save it to the USB, mount the USB inside of the Linux thing and see if it runs. Compile and run it. Whether it compiles and runs doesn't really matter to me. It's the source code I'm looking at. So here's a tree of processes on a typical Unix Solaris system where we have an ordering to this. Now this is going to be different for each version of Unix and each version of Linux. So it'll be interesting to actually see what is real, but usually it's in the triple digits, not the quadruple digits, not the triple digits, because processes, there's a lot of processes at any one moment in time. The kernel's got more processes, but it usually starts the user mode after 0 and 1, so 0, 1, 2, 3, and then we have some starting level for the user mode at that point. So process termination, if you are a C programmer, you probably have used the word exit maybe before, exit 0, exit 1. It's kind of like return, but return takes you back from a function. Exit kills the process and within inside of the process. We can also perform a wait, and that works too. What does that do? Or a sleep 5. Process just sleeps for 5 milliseconds. Or wait. You do wait, you'll hose the process right there until it wakes up. Also, a parent may terminate the execution of a child, abort the child, essentially. And then the task assigned to the child is no longer required. It goes away. We have cascading terminations that exist where the child terminates and then the parent terminates and then the parent of the child of the parent terminates. So it cascades all the way back up to the one who created it. Why do we do that? Because we can actually terminate a child without terminating a parent, or terminating a parent without terminating a child. And we can only get to these processes by their hierarchy. So if we're a parent and we create a child and then the parent goes away, we've created an orphan child process, and there's no way of controlling that process. It's out of control. There's no way of terminating it, no way of stopping it without rebooting the computer, essentially. We have processes like daemons that don't have a parent, that are out there to do print jobs and all sorts of things. So, orphan processes are not a bad thing when they're done on purpose. It's kind of like the state machine as the endless loop. Not a bad thing when it's done on purpose. You can control it, kind of thing. So, in terms of processes, the other thing I mentioned, and I'm still reviewing from last week actually, I covered a lot last week it seems, cooperating processes. Sometimes when you hear it multiple times though, it kind of makes more sense. So we have independent and then we have cooperating processes. Now if we had independent processes on a system, we might as well just have batch processing because everything is going to be running on an island of its own and we can just do sequential. Oops, okay. We could just do sequential processing, one right after the other, and they would all be independent, but that's senseless. So when we have cooperating processes, we have processes that can be affected or be affected by the execution of other processes, and they're all working together. So if we separate things out, independent, nothing can affect anybody. It's all independent, island of their own. Cooperating, they're all working together. The advantages of the cooperating processes over the independent is we have information sharing, and then we have computational speed up and modularity and convenience. So if we're saying that everything on the computer is running in the form of a process, and we have 5 processes and they're associated with 5 programs and they're equally scheduled, each program is going to run at the same speed. If we take one of them and add more processes to it and put them into the batch, that one program is going to run faster. So it speeds up the execution of the program itself, the more processes that are associated with it. So we have threading that comes with this, and we can create this abstraction through threading, multiple threads that are all associated with one process. And so then we can create a pretty interesting scenario where we have one program that's going to run faster than the other programs, if we can work it out this way. Most modern day operating systems don't work that way. Everybody runs at the same speed. So all user level processes are going to run at the same speed as as each other. And then we have kernel level processes that are going to run faster. So anything that's associated with the operating system is always going to run faster, but it's always going to run at the same speed. So producer and consumer problem, which is one of the scenarios that leads to process communication. So we have what's called IPC, inter-process communication, and then we have different classic scenarios that are associated with the running processes. Producer and consumer is one of the classic ones, where we have two processes cooperating with each other, a producer that produces something and then a consumer that reads something, that processes something. Think of a CP command. We're going to read a file, put it into memory, take the memory and write it out to a file. If we can do that, then what we can do is have one process. Are we ready? Okay, so let me pause this for a second. All right, so let's pick up where I left off. So I was talking about producer and consumer problems. So in this particular case, we have two running processes. One's producing, the other one's consuming. In that particular scenario, we're looking at something similar to, like, say, a CP command or a copy command, where we have one process that's copying a bunch of information into memory, and then we have another process that's reading that same information out of memory, but one's not waiting for the other. So they're mixing back and forth, and they're running faster than if we were to take everything, copy it all up, and then everything, pull it all down. So with two running cooperating processes, what ends up happening is we get faster processing, bottom line. However, you have to be able to make the processes communicate with each other and then do it correctly. So you don't have scenarios in which one process is constantly overriding another process and they're not talking to each other correctly. So we have different models that are associated with this. Most of them are memory oriented. So we have unbounded and bounded buffers. The buffer is the information that's being stored between the two processes. In an unbounded buffer, we're placing no particular limit on the size of the buffer. On a bounded one, we're setting a limit. We're setting a size on it. And I also showed you last time some information regarding the bounded and the unbounded shared memory. I'm going to skip through the source code examples, assuming that not everybody in here has a programming background, and it's not really going to make very much sense to you. Instead, flipping through to inter-process communication, which is what IPC stands for. So that's the mechanism for processes to communicate and to synchronize their actions back and forth. So we have a message system where the processes communicate with each other without resorting to shared variables. And then we have the IPC that is done in terms of sending and receiving in that particular model, where we've got a message and we send a message to some process, receive a message from a process, and vice versa. So it's message exchange, message passing. We also have a shared memory, where we have memory that could be seen by both processes, or a mailbox approach actually as well. So P and Q wishes to communicate. They need to establish a link between the two of them and exchange messages back and forth. So implementation of the communication link could be physical or it could be logical. If we're going to do a logical, using logical processes or physical, it depends on what kind of memory we're using, how we're going to establish the memory communication, and then whether or not we're going to have kernel level support for it. So some implementation questions usually come into place in terms of how we're going to design this. How are the links going to be established? So this is why some operating systems like Linux and Unix, as an example, that support from a kernel perspective, it supports the inter-process communication. So we have the messages to send and receive, and we have different system calls that are implemented to help processes communicate, versus operating systems like Windows and Windows, as a good example, that don't have kernel level support for this. So in a Windows environment, as you notice, you can't program with threads. or processes from a user perspective. It's because the kernel doesn't support it from a user mode. So, which is kind of interesting. So naturally, it's not going to support inter-process communication either if it doesn't support the creation of threads or processes. So it can be linked associated with one. Are you going to link more than one process together, or is it two or more processes in terms of the link? So Unix actually provides multiple process linkage, so it's more than just two. Yeah, well, you have to have two cooperating processes in order to have an inter-process communication. But you're going to have 3 or 4 or 5. Well, you can actually have a lot in a Unix system. How many links will there be? Just one link, or will there be a send link and a receive link? What's the capacity of the link? What's going to be used for? Size of the messages? Whether messages are going to flow in both directions. Can one process just talk to another process, or is it both of them talking back and forth that are going to facilitate this? And then I actually, getting close to where I stopped last time, actually, I looked at communication models where we had process A and B, and then here we have the shared memory, and here we just have the message exchange going back and forth between the two processes. And the message exchange is really called direct communication versus the indirect. Indirect is using a mailbox or shared memory. Direct is really one process sending a message to another process. And processes have to be named so explicitly. So P, send P this message, receive from Q, receive a message from process Q, and here's the message, just to receive. So the linkage is very explicit, and then we have the communication link where we have that's established automatically. And link is associated with exactly one pair of communicating processes. So between each pair there exists exactly one link that goes back and forth. And the link may be unidirectional, but it's usually bidirectional, which means information should flow both directions. So, in an indirect communication fashion, that's when we have a mailbox. So think of direct from a user perspective as instant messaging or text messaging. You're directly sending a message back and forth with a text message or with an IM. Indirect is more like email. At one moment in time throughout the day, you're going to check your email. And you're not going to get the message instantly as soon as the person sends it to you. You're going to get it a couple hours later whenever you check your email, unless you happen to be on email constantly. So it's indirect. So the messages are directed and received through mailboxes. And they're also referred to as ports. So each port might have a buffer that's storing the messages that are being received and sent on it. Each mailbox has a unique ID associated with it, and the processes can communicate only if they share a mailbox. They have access to the mailbox. So how many are you going to have checking that mailbox? Well, in the email scenario, each user has their own mailbox, and everybody has a mailbox. There's no sharing of the mailboxes normally. But in a Unix environment where you have multiple running processes, well, you could all share a mailbox if you wanted to. In fact, sometimes you do that support, technical support. One person or multiple people might be checking an email address for technical support. Hopefully multiple are, otherwise you got bad service going on. So, properties of the communication link. The link is established only if the processes share a common mailbox. And link may be associated with many different processes, and then each pair of the processes may share several different communication links. It might be different mailboxes. And links can be directional or bidirectional, so unidirectional or bi. So operations that are associated with indirect communication could be creating a new mailbox, sending and receiving through the mailbox, destroying a mailbox. So primitives are to send a message, to receive a message. Send a message to mailbox A, receive a message from mailbox A. So I believe this is probably right around where we ended last time, actually. So indirect communication here, in terms of the mailbox sharing, we have process 1, 2, 3 that share mailbox A, and P sends 1, 2, and 3 receive. Who gets the message? Interesting scenario. If it doesn't really matter who, one of the processes that have it might get it. It's kind of like how someone leaves a post-it note and then multiple people read it, but who really read it, or who's seen it, who hasn't seen it? Probably one of the most confusing parts of this form. So in terms of the solution, allow a link that's associated with at most 2 processes. So you're only sending it to one person instead of sending it to a group. And then only allow one process at a time to execute a received operation, and then allow the system to select arbitrarily the receiver. And the sender is notified who the receiver was. So let's talk about synchronization in terms of multiple processes, and I believe this is the new information for this week. But it kind of helps to go over, because we only meet once a week, it kind of helps to review sometimes, and this is an important lecture to review. So we have blocking and non-blocking, and this applies towards CPU scheduling, I/O scheduling, process synchronization, all three concepts. So throughout the next 3 or 4 chapters, we're going to hear blocking I/O, non-blocking I/O, blocking CPU, non-blocking CPU. When you're using the CPU for something, the process is going to block all other CPUs. Only one person can actually use a CD-ROM drive. I/O is normally blocking. Because if you interrupt I/O, you're going to spend more time interrupt, restart, stop, start, stop, and if you just let the job continue, because it's a slow process. CPU, however, doesn't necessarily have to block. So what's meant by blocking? Blocking is synchronous. Non-blocking is asynchronous. And then you're wondering, well, what's synchronous versus asynchronous? Synchronous is multiple things happening simultaneously. It's not one at a time. Asynchronous, it's one at a time. In an asynchronous operation, in a non-blocking, which is asynchronous, we have something happen, something else happens, something happens, something else happens. We don't necessarily know the timing of this, just one thing after the next. So message passing can be either blocking or non-blocking. Blocking is associated with synchronous. Blocking send has the sender block until the message is received. Blocking receive has the receiver block until it is available. The way you think about this is go with the walkie-talkie environment. We have 2 processes that are communicating. You guys are familiar with walkie-talkies? Or even, in the old days, somebody in a blocking mode, if the speaker is speaking, the receiver is listening. They can't speak simultaneously. So even though it's synchronous, it's all happening one after the other in line. So it's like sequential synchronous. Hey, how are you? And the person comes back and says, I'm fine. And they go, okay. And then they press a button in the walkie-talkie mode. One can talk, the other one. The button is a blocking mechanism. So processes can do this to communicate with each other. Or in a non-blocking mode, non-blocking, the send has the sender send the message and then continue. You just say, hey, here's a message. It's like email. You send it out, you send it out, you send it out. And then you can continue and do other work. You're not sitting there waiting for the response. If you're sitting there waiting for a response back, you're doing it incorrectly. You shouldn't be sitting there waiting for a response back. That's asynchronous mode. And non-blocking in the receiver has the receiver. The receiver receives a valid message or it receives nothing. No. Hey, you might want to check with the front desk. They just did attendance. If you want to get credit for being here, you might want to investigate that. So, buffering. So, the queue of a message attached to a link, limited to one of 3 ways. So, if we're going to buffer, which is the best way of actually keeping track of these messages, otherwise we're going to lose them. So, buffering is kind of like the voicemail, kind of spot to save the message at. Oh, this guy's going to have the same problem, but you know what? I'm not even going to bother. They'll get it in the next couple weeks. They figure out, how come I'm not in attendance? 0 capacity, 0 messages. Bounded capacity, infinite length of end messages. The sender can wait until the link is full. Hey, there's plenty of room up here. I don't know why you're going to stick a chair in the back. Actually, there's a spot right over there in the corner, too. But you know what? You might want to check with the front desk because you just missed the attendance. All right. All right, so just know that the buffering can be of many different sizes, and it can be facilitated in many different ways, depending upon the need. So as I mentioned before, when we have inter-process communication, we set up the communication between the channels, and here we have the client-server communication. That can be set up. I'm not going to bother with this one either. So in a networking class, you usually talk about sockets. And then you have buffered information that's connected with the sockets. So in a socket, we have, it's a Unix system call normally that creates a socket. It's bound to a port, IP address, and we send and receive back and forth through the socket. The socket's sort of like the mailbox in that scenario. And then we have this thing called remote procedure calls, or RPC, which is the original form of shared communication, where we have procedures that are called from one computer to another computer that are done through processes, where one process would signal to another process on another computer and say, hey, could you run or do this or do that? And then we have communication that exists between multiple computers or multiple sockets or multiple ports. And then along came RMI, remote method invocation, which is implemented in Java. All three of these forms use multiple processes to facilitate the communication, and the multiple processes are running from, in this particular case, multiple computers. So networking, in a nutshell, is nothing more than a bunch of processes communicating with each other from different computers. And they're using something to communicate, a port or a socket abstraction. So here's our socket abstraction, which is the primitive kind of form. So if they're not using a socket, they could be using what's called a, let's say, an RMI manager or something, where we have a registry where we're keeping track of different computers and different RMI engines, and we basically are loading, it's kind of like a JVM, but it's a manager that's keeping track of the communication between the different computers. So if you take Java EE, you'll learn more about RMI in terms of a network, or take a networking course. You'll learn more about that particular concept. But it's hard to talk about operating systems without talking about networking, because operating systems are generally networked. So, sockets. That's the primitive at the beginning of time. We had, beginning of Unix, we had sockets. So a socket is defined as an endpoint of communication, and concatenation of the IP address and the port. So here's a socket example here. We still have sockets today. Every single computer's got a socket on it. We all have ports. We may not necessarily be using all those ports, but we all have ports on our computers and we all have sockets. So communication consists between a pair of sockets that might be working. So here's an example of socket communication, and where we have host X, and then we have a web server over on the other side, and we have a socket here that is bound to an address, and we have a socket here that's bound to an address, and we're just sending information back and forth through inter-process communication, which is why I'm mentioning this at this point. In the remote procedure calls, the RPC model, we have a procedure call between processes on networked systems. We have this thing called a stub. So we have a client-side proxy, the actual procedure on the server, and then we have the client-side stub, locates the server, and then marshals the parameters. So then we have server-side stubs that receive a message. This does nothing more than the format for the messages and the abstraction of keeping track of the sending and the receiving, packing, unpacking, marshaling, performing operations and procedures on the server, back and forth. So here's an example of the execution of an RPC, where we have messages that reside between the client and the server. So on one end we have the client, the other end we have the server, and then we have our message exchange that's going back and forth. So not a networking class, so I'm going to just go through a little bit briefly on these concepts. But here's the remote method invocation, RMI, which is the Java version of the client server and distributed processing, essentially. And so they have the Java mechanism similar to RPC. RPC is the Unix first form of it, and then RMI came at second, so it's just the Java form of it. So we have a JVM on one, a JVM on the other, and we invoke different methods for different objects on each one of them. What does this do? It takes advantage of economies of scale. And so we have many different clients connecting to a server. Well, they're not always creating their own instances of all these objects. They're sharing objects. And then they're invoking methods on objects that already exist on multiple computers. So it basically connects multiple computers together. So.